with all the things we've seen in the previous videos, it's now time to define space, or actually redefine space, because we already have some ideas on what space is, but now we have to define it with a very objective way, okay? And that's what we're going to try to do here. And also we'll, I think, understand why now we have to talk about space-time, not just space. First thing to do is to look at what we should do in the mathematical world. There are two isomorphic worlds, the physical world and the mathematical world. Well, in the mathematical world, as soon as we want to measure or assign a value to a property, we need a reference. Actually, of course, it's true in the physical world as well. But let's focus on the mathematical world first. This reference, which is called a frame of reference, especially in the physical world, corresponds to the basis in vector spaces. Basically, when you have a vector like this and you use 3 vectors here for a 3D space, then you can assign, elements of this vector here with some values, okay? Pretty easy stuff, right? Actually, everything I'm going to talk about in this video seems pretty trivial, but you have to follow it very carefully, and then we'll see where it leads. So in this case, this means that vector v is equal to 3 times vector x, and 2 times plus 2 times vector y, and plus 5 times vector z. Okay, these are the basis vectors. Now, let's take an example here with only 1 dimension, to simplify things, but the results would be the same with 3 dimensions or 5 dimensions or 20 dimensions. So, okay. Here we have a vector which is equal to 3 times x. X is our basis here, our reference, okay? So if we look at it, here we can see that v is equal to 3 times x. Okay, no problem. Now, in the mathematical world, what that means is, given the reference, the basis of vectors, here 1 vector x, we can assign a number, in this case 3, or a 3D vectors, if it's 3 dimensions. And we can assign this number to the position, okay? So we can say that this position here is position number 3, okay? Good. So you can assign a value to the abstract concept of position, and which is part of the object's current state, as we've seen before. Okay? Pretty easy. Okay, piece of cake. Now let's see what happens in the physical world. Here, okay, we have this object here, and now we want to compare it, this object to a reference. Okay, let's forget for now about, the 3 units here. We can focus on 1 unit, and then the rest is pretty trivial. So we'll assume that we want to make sure that this object has a length equivalent to our reference here. And now, what does that mean? How can we measure it? Remember, we don't know much for now. We don't know what space is and how to measure it. We don't know what time is. We only know about simultaneity and states. Okay, so in our case here, let's zoom in. What we want to do is to set up something in the physical world so that it will allow us to say this object has a length of 1 reference. Okay, so how could we do that? Well, what we've seen before about simultaneity, and we also defined what a middle point was, we can use it here. So for instance, we could say, okay, here I will take the middle of this segment here, okay? And I will do the same here. And then between those 2 points here, I will take the middle of this segment there, will be here, okay? And now I'm going to send, from here, a light here, and it will go to this point, and then there will be some mirrors which will transport it to this point and to this point, and the same here, same here, same here, same here. Let's look at what happened there. Okay, here is a light, and then we go, these ways. You can see the arrows here. Okay, and bim, we resave them back. And if we see only one event here when we receive the results of all this traveling, then we will say that the length of this object is the same as the length of this reference here. And that's it. And that's how you measure space. Because, if you take this as the origin, for instance, then you can say the position in state here, will define the reference unit. Okay? And then you can compare any object to that reference. And that's how you measure space. And therefore, that's how you reference and define space, And that's key, because that also shows you that, in order to define space, you need an object, you need a reference, Otherwise, it doesn't make sense. And it's useless. Okay? So let's focus on that. Now, let's see. Space can thus be defined like any other observable properties, in the physical world through the use of a measurement, by measuring things and the way we've seen before. As you could see, light is a pretty important concept here which is used for simultaneity and for, to define space, for instance. And we'll see why we chose light in the next video. If you want to assign a value to its measure, then you need a reference. As usual, we've seen that. The same in the mathematical world with the basis of vectors. Well, here in the physical space, you also need a reference. Finally, the definition is very much linked to the concept of simultaneity, as we've seen, because all the things we have designed in order to measure space were very closely related to the notion of simultaneity that we've seen before. And that just like time, as we will see, and this is why space and time cannot be dissociated. They're actually defined in the same way, using the same concept, the concept of simultaneity, which is very important. And so they're very much linked together. And so it makes sense to call them space-time. Okay? And that's wonderful. Okay, now even better, we're going to define time and start to see new things that we've never seen before. Fascinating.